Hello. What it do, homie G's? So, it's been like 3 years since I made a video, so I don't know why I'm showing my face, but I'm actually going to show my face to you guys now. Now you're going to really know how awkward I am. Alright, anyways, in this video, I'm going to be talking about graphing rational equations, as you can see clearly on your note sheet that you should have. If you don't, come talk to me. Alright, so I'm just going to roll through it. Rational equations are similar to our 1 over x graph. 1 over x looks like something beautiful like that, right? So we're going to kind of have something like that as far as getting closer to a horizontal asymptote and a vertical asymptote, right? So that's what we're going to be doing. This is used in optics, logarithms, not logarithms, that was a lie, all sorts of different things though. So with my x-intercept, right? Still finding an x-intercept, I like how I find an x-intercept, right? I'm going to put in 0 for y, right? So if I put in 0 for y for this, solving my x-intercept, let me grab another piece of paper, super fast, wham! Like a magician. Now I'm going to freak out my neighbor. She's going to come over here. Okay, maybe she just doesn't care. Anyways, so for my x-intercepts, if I put in 0 for y, this would mean I have 0 equals 3 over x minus 4. So if I multiply by x minus 4 on the other side, I have 0 equals 3. Now, 0 doesn't equal 3. That's not as a true statement. So if that's not a true statement, that just means I don't have any. I have no x-intercept, so I'd write none. For my y-intercept, right, I'm going to put in 0 for x. So I have 3 over 0 minus 4. So that should be negative 3/4. So I have 0. Negative 3/4 is my y-intercept. All right, moving on. Vertical asymptotes. Let me write some definitions for you guys real quick. You may want to pause the video or something and write this down, but vertical asymptotes are our impossible x values. They happen when we divide by 0. So if I look at my function, the value of x that would make me divide by 0 is when x is 4. That is my vertical asymptote. So on my graph down here, I would have a vertical asymptote when x equals 4. So 1, 2, 3, 4. Right, so there's my vertical asymptote. All right. So essentially, you're just setting the denominator equal to 0 and seeing what values of x would make it 0. Those are the values that you cannot have. For our horizontal asymptote, let me write a few things for that as well. All right, my little chitlins, I changed rooms. That was super fast! You have no idea how I did it in like 2 seconds. And I got these fancy tiles. Oh, they're so pretty! Okay, so horizontal asymptote rules. The horizontal asymptote represents the end behavior, essentially. So if I were to put in infinity or negative infinity for x, it represents what y values we are going to as we go out forever. Woo! So I'm not going to get into like that infinity too much. If you want to come ask me in person, that's cool. And I'm more than happy to talk to you in person about this. But I don't want to like bore everybody with my super fun math talk, which is all this video is. It's just math talk. Anyways, all right. So horizontal asymptote, again, represents the end behavior. So if I know the horizontal asymptote, I know what my function is going to out as I go to infinity. Given a rational function, something like this, ax to the n, where n is the highest exponent in the numerator, bx to the m, where m is the highest exponent in the denominator. If my denominator power is bigger than my numerator power, this is also called bottom heavy, y equals 0 is my horizontal asymptote. It's going to go to 0 as I go out forever. If they are the same exponential power, which we'll see here in number 2, a divided by b is my horizontal asymptote. So just the coefficients of those highest exponent terms. If it is a greater exponent in the numerator, we're going to have something called an oblique asymptote. Super cool. We'll talk about it in just a little bit. All right, so for this one, I see I have no x's in my numerator. I have an x to the first in the denominator. So the denominator has a higher power. If the denominator has a higher power, y equals 0 is my horizontal asymptote. And I have a horizontal, not an oblique. So to graph that beautiful little thing, I have my vertical asymptote at 4. I also have a horizontal at 0, which you can't see very well because it's on the x-axis. I also have a y-intercept at 0, -3/4. So I have a y-intercept here. Yes. I have no x-intercept. So now, I know that I don't have any x-intercepts. So as I go this direction, my graph should get closer and closer and closer to the x-axis. Those values are getting smaller and smaller. I know, again, I don't have any x-intercepts, so I'm not crossing my horizontal asymptote here. So I can go out and get closer to my vertical asymptote there. On this other side over here, I have no idea what is going on. No clue, right? So what I can do is this is 1, 2, 3, 4 is my vertical asymptote. So say I want to check f of 5. I want to see what kind of y value I get. Some graphs will be up here. Some graphs will be down below that. Usually it happens if we have like an x squared in the numerator, but we don't here, so it's probably going to be up top. But let's check. Let's make sure and actually be careful with what we are doing. So if I put 5 into my function, that is 3 over 5 minus 4, which is 3 over 1, so that is 3. So if I put the ordered pair, 1, 2, 3, 4, 5, 1, 2, 3 on my paper, this graph will go closer to my asymptotes as I go. If you don't believe me, you want to pick additional points, you are more than welcome to pick additional points. All right, moving on. So my domain for this thing is all the x values that I cannot have is what I can't have. So the only thing I cannot have is 4. So I will say my domain is -infinity to infinity as long as x is not 4. Is how I will state that. For my range, the only y value I can't have for this is 0. So likewise, I have -infinity to infinity, but y cannot be equal to 0. And that's it. That's my domain, and that's my range. In behavior, so I'm looking out as I go forever. So as x approaches infinity, and as x approaches -infinity, I'm going to state what my function goes to. My function name is f of x, so I will call him f of x. Call me what my name is! I'm sorry that I just yell all the time. It's your fault. All right, so as I go out to infinity, I'm getting closer and closer to that horizontal asymptote. Again, the horizontal asymptote represents the end behavior. So I know as I go out that direction, I'm going to 0. As I go to the negative direction, my y values are also getting closer to 0, so I'm getting closer to 0. All right, so now, behavior at each point of discontinuity. I have a discontinuity right here. This is the same thing that we were doing with the piecewise functions. Here's my discontinuity. So I am approaching, as x approaches 4 from the left, x approaches 4 from the positive side, and I'm going to state what my y values are going to. So let's see. As I approach 4 from the left, so I'm going from this side, looks like it's going to -infinity. As I go to 4 from the right, looks like I'm going up forever, so I'm going to positive infinity. That's it. Okay, that is our first rational function. Let's do some more! Are you going to make that slow-mo? Maybe. YouTube. All right, x-intercept. If I put in 0, I will have an x-intercept of 3 over 2, 0. My y-intercept would be 0, -3/2. My vertical asymptote, the x value would be -2 to make that 0 my denominator, so I'd have x equals -2. And my horizontal asymptote, so again, think about your powers. X to the first, x to the first. So since they're the same power, I take my coefficients. 2 divided by 1 is 2, so I have a horizontal asymptote at y equals 2. Now for my domain. I can do this before I even graph my function, right? Because the only thing I can't have is my vertical asymptote. So I'm going to say -infinity to infinity, where x cannot be that -2 value. Range I can also do, because it's the normal one, right? So I can say -infinity to infinity, but I can't have my horizontal asymptote, so I'll say y cannot be 2. And behavior I can also do before I graph this. So I can say as x approaches -infinity, and x approaches infinity. Check your function name. My function name is f of x, so I will call this f of x. f of x approaches. So again, I'm approaching my horizontal asymptote. That is the definition of a horizontal asymptote. It represents the end behavior. How'd you like that? I know you liked it a lot. Right, so I should be getting close to my horizontal asymptote in both directions. Okay, behavior at each point of discontinuity. I know the discontinuity is at -2 because that's where my vertical asymptote is. Right, so I can say at least as x approaches -2 from the left and x approaches -2 from the right, my function should be going to something, and my function should be going to something else. I don't really know that well. I could probably figure it out, but I don't know that well what it's going to. So I'm going to go ahead and graph this and see what my graph looks like. So I'm going to put everything on there, put my x-intercept on there of 3/2, 0, and I have a y-intercept of 0, -3/2, so I'm done there. I have a vertical asymptote at -2. Right, there's my vertical. I have a horizontal at y equals 2. There's my horizontal. So it looks like I should have a graph going something like that, getting closer to my asymptotes. I have no idea what's going on this side of the vertical asymptote, so I will choose f of -3. I think that's what that number says. All right, so if I put in -3, 2 times -3 minus 3 over -3 plus 2, so that is -6 minus 3 is -9 over -1, which is 9! Oh yeah, bye-bye! All right, so I have -3, 9. It's -3, and I'm up at 9. Again, I'm going to get closer to my asymptotes as I go. So something sort of ish like that. So now, my behavior at my discontinuity. There's my discontinuity, right? My vertical asymptote. So as I get closer to it from the left side, or the negative side, looks like it's going up forever, so I'm going to infinity. And beyond! All right, and as I go from the positive direction, I'm going down forever, so my y values are going to -infinity as I go. Bam! Alrighty. Let's see here. Yeah, I want to do this one. I'm going to do 3, but I'm going to skip 4. I want you guys to try 4. So, next thing with these, quadratics are kind of weird sometimes with these. So what I would do is if I see a quadratic and I can factor it, weird things happen sometimes when I factor it. Right? So you'll see in just a little bit, I'm actually going to have to do number 4, when that's going to happen. It'll happen in number 4. Will it? No, I'm lying. I'm going to skip number 4.
Make up your mind, Mr. Bike, come on!
Alright, so looking at my factors, nothing will simplify there, so I'm just going to go for it. So for my x-intercepts, if I make y 0 here, right, then I would have 0 equals all that junk. Alright, and then I can multiply by the denominator, so I have 0 equals x plus 1, x minus 1. Alright, so I should have 2 x-intercepts at -1 and 1. So I have 2 x-intercepts, -1, 0, and 1, 0. For my y-intercepts, right, if I put in 0 for x, I would have -1 over -9, so 1/9. Beautiful. My vertical asymptote, I'm going to have 2 x values that if I put it in, will make my denominator 0. I'll have -3, 0 times -6 is 0, and I will have +3. So I have 2 of them. What? That is just crazy! Right, so I'm just going to say plus or minus 3. I have a horizontal, because my powers are the same, they're both squared. I have a 1 in front of that one, a 1 in front of the denominator one, so I have 1 divided by 1, which is 1. My domain, again, I can do, it's just not the vertical asymptote, so -infinity to infinity, where x cannot be plus or minus 3. Right. And the range, I'm going to wait on that one because I don't know what's going to happen with these 2 vertical asymptotes. So, put your x-intercepts on your graph. So I have there and there. I have a horizontal at 1. I have a verticals at 3 and -3. That was weird. You guys hear that? Strange. They did something weird with the bell. All right. So now, and then I also have a y-intercept of 0, 1/9. So somewhere in there. So that middle part looks like my function, since I know I don't cross the x-axis again, they have a multiplicity of 1, should be going closer to there, and should be going closer to there. So I'm getting closer to my asymptotes as I go. Now I have no idea what's going on the outside here, so I'm going to plug in some values, right? So f of -4, so that would give me 16 minus 1 is 15 over 16 minus 9 is 7, which is bigger than 1, so I'm somewhere above here. Again, closer to our asymptotes as I go. Beautiful. And f of 4, if I put in 4, it's going to be the same deal for that 15/7. Somewhere up there. What is that? 2.142857 repeating? 142.857 repeating? Check out the divided by 7 tricks. Pretty cool. Alrighty, so there's my graph. So now check it. I have 2 points of discontinuity. So I'm going to kind of split this up into 2 sections for you because I have a discontinuity at -3. I also have a discontinuity at 3. And my range, I'm glad I didn't do it because check it out. There's this little gap right there between 1/9 and 1. So for my range, I need to go -infinity to 1/9, where that is included. And then I go from my horizontal asymptote to infinity. Interesting, right? Because I'm going up to a high point, and then it turns around. So I kind of have a vertex-ish right there, but it's not really a parabola because it's going towards asymptote, so it's not the same behavior. And then I'm going closer to 1 as I go out forever. All right. So my behavior of the discontinuities I have as x approaches -3 from the negative side, and x approaches 3 from the positive side, -3 from the positive side. My function is going to, let's see, so -3 from the left is going to infinity. -3 from the right is also, well, it looks like it's going to -infinity, so I'm going down to -infinity there. Okay, as x approaches 3 from the left, and x approaches 3 from the right. All right, so 3 from the left looks like it's going down forever. So I'm going to -infinity. 3 from the right, it's going up forever. So I'm going to infinity. And then my end behavior I need to state as it gets closer to the horizontal asymptote. So as x approaches -infinity, f of x approaches 1, x approaches infinity, f of x approaches 1. Cool. All right, I'm going to skip 4 in this video. You guys can try that for homework. And I want to do number 5 with you. So check it out. I have a denominator that I can factor, so I'm going to factor. Whoa. So I have a factor that's the same. So these can divide out. However, this factor is still a part of my original function. So I know that I can't have 1, but if I were to divide out this factor, this would give me 1 over x plus 1. But still, again, I know that I cannot be positive 1. So x cannot be 1. And what this does is this creates something called a hole. This is where our removable discontinuities will come from for graphs like this. So a hole, a removable discontinuity, let's see, solution factor divided out. All right, so for this instance, my whole would be when x is positive 1, right? Because if I got rid of x minus 1, the solution of that factor is 1. The other cool thing we can do is I can figure out what point that is by taking this 1 and substituting it into my original function. So if I do 1 over 1 plus 1, that is 1 over 2. So I will have a whole exactly at 1 1/2. So on my graph at 1 1/2, I know that I will have a removable discontinuity there. It's going to be an open circle, and hopefully it's going to go around it. So from this point on, I'm going to do all of the rest of this equation, these components, these characteristics, with my simplified function. After you simplify and you determine that there's a hole, put it on your graph, use the rest of it, words, come on. Find the rest of your characteristics with the simplified function. So I'm going to use this to find everything else. So my x-intercept, I will have none. My y-intercept is 0, 1. My vertical asymptote is x equals -1. My horizontal is y equals 0 because the denominator power is higher. The domain I'm going to wait on, the range I'm going to wait on, and I'll wait on all the rest of this stuff. So graphing what I know so far. I have a vertical asymptote at -1. And I have a horizontal at 0, so I got to remember it's there because it's black and it blends in. And I have a y-intercept of 0, 1. All right, so getting closer to my asymptote as I go, and getting closer to my asymptote as I go. Got to figure out what's going on over here, though. Whether it's below or whether it's on top, it's probably going to be below because it's a simple function. But let's see, f of -2. I have 1 over -2 plus 1, which is -1. So I have -2, -1. I have a point right there. And I will get closer to my asymptotes as I go. Beautiful. All right. So now domain. Be careful here. There are two x values that I cannot have. I cannot have -1. I cannot have +1. So I'm going to say -∞ to infinity. However, x cannot be plus or minus 1. My range, there are also two y values that I cannot have. I cannot have my horizontal asymptote. I also cannot have the y value of my hole. So usually we'll have like a hole spot. My hole was at 1 1/2. So I'm going to have -∞ to infinity, but y cannot be 0 or 1/2 because there is a hole there. It does not pass through over here to 1/2 on the left-hand side of my graph. So I cannot be at that 1/2. In behavior, still your horizontal asymptote. My function goes to 0. X approaches infinity. My function goes to 0. Right? Nothing changes about that. My behavior at the discontinuities. So here, make sure you list your infinity one. I'm not going to worry about that one right now. I want to talk about our other discontinuity. Yes, you would list both. So as blah, 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 and blah, 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 blah for my infinite. I'm going to let you guys do that. Now the removable, I have a removable at 1. So I'm going to say, as x approaches 1 from the left and x approaches 1 from the right, my function values, well, I know what the whole would have been if there was a value there, right? So it should, as it goes to the left and to the right, be approaching that same value of 1/9. Even though there's this continuity, they're approaching the same value. All right, it's like I plucked that point out of my graph. All right, and that's pretty much it for that one. Let's see the next one, same sort of idea, just another hole. I'm gonna let you guys do that one. All right, we got one more and then we're done. One more and then we're done. Holy cow, this is already a 25-minute video. Let's bust some butt. All right, so factor. Well, dang, there are no common factors, so I have no holes. X-intercepts would be 2, 0, and -1, 0, y-intercept will be 0, negative 2, positive 2. My vertical asymptote is x equals 1. Now, for the horizontal, going back to our rules. If n is greater than m, I have an oblique asymptote. So how do we find that oblique asymptote? What we do with an oblique, I'll do it over here, I'll make another definition. Oblique, hang on. So you do the division that you see, and you're going to ignore the remainder. The reason that we ignore the remainder is because it's going to infinity, so if I throw infinity, if you want to know about that, let me know in class. All right, so I'm going to do the division I see to find my oblique asymptote, and what I mean by that is I see this division right there. I see x squared minus x minus 2 divided by x minus 1. So to find my oblique asymptote, the easiest thing to do here would be do synthetic division, so 1, negative 1, negative 2. So I'm going to carry down the 1, 1, 0, 0, 0, not 0, negative 2, but it doesn't matter anyways. I'm dying! This would be y equals x, right? Y equals x, and then minus 2 over x minus 1. But again, I'm going to ignore the remainder. I don't care about it. So I have an oblique asymptote at y equals x. That's not an x. Right, there's an x. So if I were to graph that oblique asymptote, I have an asymptote that is acting like the line y equals x, which is pretty cool. You can have a quadratic asymptote, you can have a cubic asymptote, you can have any type of asymptote. They're kind of interesting. Vertical at 1, so I'll draw a vertical at 1. And then I have a x-intercept at 2, 0 and negative 1, 0. So, cool thing, that's pretty much all we need. I should have a y-intercept as well, right? 0, 2, yeah. Right. So, I'm going to get closer to my asymptotes as I go. So, my oblique, I'm going to get closer to that in both directions. I'm going to get closer to my vertical, and then closer to my vertical, and closer to my oblique asymptote. Interesting. So check it out. The range, it goes up and down forever, but the domain has some restrictions. So the domain, still I cannot divide by 0, so I'm going to say negative infinity to infinity, but x cannot be 1. And my range we saw is negative infinity to infinity. Now the end behavior would be as x approaches negative infinity, f of x approaches, and x approaches infinity, f of x approaches. So let's see, as I'm going to the left forever, so negative infinity, I'm going out this direction, going to the left. My y values are going down forever to negative infinity. As I go to the right, as x goes to positive infinity in that direction, I'm going up forever to infinity. That's it. Don't get freaked out by the end behavior with these obliques. Still, it follows the end behavior for an asymptote. So if I think about the line y equals x, that has the same exact end behavior. Behavior, the discontinuity, you only have the one discontinuity of the vertical asymptote. You guys can do that. I believe in you. Same sort of idea with number 8. You guys can do that as well. All right, I believe that's it. Try to finish that up, as well as obviously the worksheet for homework. Hopefully this video was helpful for you guys. I have to try. I always end on the monkey. If you haven't watched videos yet, you have to end on the monkey. All right, I'm sorry this was so long, but I'm here for you guys. This is everything. Everything.